So hit the record button. Okay, we're recording now.
Okay.
So let's go ahead and look. You're talking about I usually look at the homework one, so that way when I answer it, I rarely make mistakes, but it can sometimes happen. You're talking about chapter 5, part 3, are you?
No, I think it was chapter 4, part 2.
Okay, chapter 4, part 2. Let me pull up that one right here. Okay, I'm going to pull up that assignment, and then we can go to viewing my screen, and we can talk about it and make sure we get everything clarified.
Okay.
Okay, we got some, this is quantitative displays of data. So I'm going to go to share screen. Desktop. Okay, so here we go. This is the assignment you're talking about, and you're talking about this last one right here. Yes?
Correct.
So this last question is a time plot of data. So with the time plot of data, you're looking at a time axis here on the bottom, and so a time plot is a quantitative display of data with the time axis as the x. And there's actually a little bit of a cheat to this one.
Okay.
The cheat to do it is you can eliminate one of the wrong answers by noticing the wrong scale at the bottom. The 1941 to 2003 is the wrong scale.
Oh, okay.
And then looking at, you don't want to, like on the test, this wouldn't, we're not just trying to learn how to cheat and answer one question. But always check the scale is a good thing. Like, okay, is the proper scale? Okay, we see this is the wrong scale.
Right.
Now, what you can do is, now that you've identified the right one, which is this one over here, which has the same scatter of points with the right scale, I like to look at the points themselves. If you notice, it starts out 2, 2, 1, 3, 3.
Mm-hmm.
So if you read the points here, you'll see 2, 2, 1, 3, and then the next one is 3. It's hard to see because it's hard to tell where they go.
Right.
You kind of see 2, 2, 1, 3, 3, and then the next one's 0, 2, 1, and you can check 0, 2, 1.
Okay.
You can go to the end of the data and kind of check 3, 7, 7, 6, and do 3, 7, 7, 6. And there's kind of a upward trend of this data. It might slope or something, but we get into that in chapter 6. I think chapter 6 is core. But that's the best way to check that question.
Okay, now I wish I'd have known about the date. That's very...
It's the trick on the question. It would make
sense.
Yeah.
Because I'm counting and looking and making it bigger and putting it on jump plot and putting it up next to each other.
Wow.
Yeah, it was... And yeah, that's okay.
Believe me, I've worked these. If they ever change the homework assignments, I'll probably be in trouble because I've worked 50, 60 times. It's pretty crazy. I'm going to turn off my speakers here real quick. There we go. I had a little sound in the background. Yeah, so I think this question is one of the big areas of knowledge to gain from this, other than figuring the right time plot, is that a time plot is a quantitative display of data. So it's bivariate with the x-axis quantitative time and y-axis quantitative whatever you want. We go back to other quantitative displays like box plots here, which are univariate. And actually, this is it is not bivariate in the sense that you're analyzing one variable in contrast to another, but it is multiple box plots are kind of bivariate. We'd call them side-by-side box plots, as we've talked about. So you can do side-by-side box plots to see more than one box plot at a time. But a real bivariate display is usually going to kind of give you something like this, like a scatter plot is more of a true bivariate display. And the first one is a summary table of the quantiles.
Right. Now on this one, when this first one, when it asks about the skew, the girls or the boys skew, it's hard to see that skew when you put it into jump because it's just like even bars. So
yeah, I'm trying to. If you go to, I think a lot of people figured it out when you go to make tab delimited. I always use that option right there. Make tab delimited copy. On Macs, it can get a little bit weird. On a Mac, it can sometimes, I don't know, for some reason when you paste things in Macs, you'll sometimes get these blank rows. I don't know if you have a Mac, but some people might.
No, I have an HP actually.
Oh, good. That's what do I have? I have a Lenovo.
Okay.
No, I like Macs a little bit, but I grew up on PCs. We didn't have Macs in the 80s. I mean, we did.
I understand.
It was Apple IIes.
We didn't have any of this when I was your age.
Now, when I grew up, it was Apple IIe's. Like I grew up in the '80s, so but no. Before that, there was like no computers in school. You're right, like '60s, '70s, no computers. Like computers,
or they were huge.
the size of a room, like a refrigerator. Yeah. Oh god. Now this is more powerful than anything in the '80s.
It's funny.
Craziness. So the problem with doing jump analysis on this is you're actually analyzing the quantiles of the box plot. So I'm trying to remember if I do that in the videos because actually when I first started doing these assignments, I didn't realize here that it says that these are the 5-number summaries.
I had to read that 3 times before I realized because I was kept trying to get the 5 numbers. And then it dawned on me, oh, this is the 5. These are the 5 numbers. Yeah.
It really was, I would say, after my first year of teaching this class and doing this problem, I was like, oh, this is the 5-number summary. So with that in mind, spacing between the quantiles tells you where the data is spread out because this represents the minimum person, the maximum person, the minimum person, the maximum person. So you want to look out. This question is not one of my favorites. I do find it to be a little bit tricky. You know, I think some questions exemplify what we're trying to learn more than others. There's no perfect question. Someone out there probably loves this question. Which group had the highest score? It's going to be the boys. No, excuse me. The girls. They have reverse boys and girls. Which group had the greatest range? So we need to do max minus min, which it's looking to be the girls have the greatest range. Yeah, the girls have a higher max and a lower min, so by default they're going to have it. Greatest interquartile range, the boys have an interquartile range of 1, and for anyone watching the video, this is because this is Q1 right here, and this is Q3. Just have the 5-number summary, min, Q1, median, Q3, and max. So the range of the interquartiles is 1, and then over here it's 1.2.
Right.
So the girls have the greatest interquartile range. And then the skew question I think is coming up, which is my least favorite question on here. I find it to be deceptive, and I'd rather look at it. Skew, I'd rather look at a histogram. Box plots are not the best for skew. So let me take a look and see if I can get this answer, because I have missed this one before. I do find it to be deceptive. You got to be really careful. The guys right here, if we look at these distances, this is a spread of 5. This is a spread of 5. If I were doing this problem and worried on a quiz, I'd write down 0.5, 0.5. That's how spread out that is.
Okay.
And then 1, a spread of 1 right here, and this is a spread of 0.8. I'm just doing the distances they are apart. So we have 0.8, 0.5, 0.5, 1. Now here's 1.2 and 0.5. So actually this seems a little more spread. And this is 0.7. Well, skew, if it's symmetric, like, I really wish we had a histogram. It'd be the best. Like, there's one question I don't like on this. The rest of it is beautiful because it really wants you to understand certain things. So we said 0.8, 0.5, 0.5, 1. That's a little bit symmetric. The only real skew to it is the right is a little bit skewed more. The right is more pulled out. This is 1.2, 0.5, 0.7, 1. They're kind of oddly skewed. Well, okay, let's see here. It's going to be the girls or the boys, so you got a 50-50 shot either way. The girls are more skewed because the quantiles are not the same distance from the median. The boys are more skewed because the quantiles. So the girls, I think, have more differences in their quantiles. Neither of them have the same distance, which I don't like. But the boys is like 0.8, 0.5, 0.5, 1.
Right.
Which is more similar. Got it. I hate it because when it changes the numbers, sometimes it's a little bit too close for my liking. I don't think it exemplifies. In these questions, I think we need to go for, like, it really just hits the meat of the topic. And if you read what it says, skew is when the quantiles are not evenly spaced out. Okay. And that kind of gets to the point. And I wish it just had the girls being like 2.5, 3.7, 4.2, 4.9, 6.8, and then that you could identify a right skew right there immediately.
Right.
That's right skew. So yeah, but maybe that would be too obvious then. So, but yeah, I love every part of this question until the last part where it gets like iffy shady.
Right.
What else this week do you have questions on?
I don't know. It's just trying to get into a rhythm with this and management and reading and all and trying to work and all that good stuff.
I think, let me pull up The ones that really start getting people, and so I'll show some of this if you have questions, is the 5.3 stuff. Is when people really start to. Have you done 5.3 yet?
No, I have not. I'm on 5.1, doing the Z and the standard deviation. That one's not too bad. I think I've got the formulas down. So
the biggest thing is the 68, 95, 99.7, which I really try to make clear that those should almost be like that. So we'll incorporate, if you want to talk some more, I'll go. Do you want to talk about these things? Or
Sure, that's fine.
Yay! I get to teach.
Yeah, exactly. I know. I kind of miss the classroom. This is very good, and you and Mark have both done a great job with these. But I do kind of miss being there and more hands-on, I guess, especially with this.
I'm worried as we get further down the road that maybe people won't like. I think you're doing everything, but I'm worried of other students who might not pace themselves to where on Saturday and Sunday they're up at 10:30, 11 p.m. and they're like, I gotta learn everything right now, and it's like, oh, this is a summer course where you need to have a rhythm.
Yeah.
Mentally marinate a little bit.
Yeah, you got to find it. It's the second week, so I think I'm finding it, but
I know everything. It doesn't really crank up. We're kind of right now. The second and third we're reaching the point at what it's going to be at. The first week was easy. Second week is showing more what this course is going to be like.
Yeah.
Also, I have to send out some emails if students aren't not like. I just want to be like, hey, if you're not doing the work now when we come to the test, because I don't want to have 50% fail.
Right.
I really like these questions because so far it seems like you've worked a lot with the empirical rule. So with the empirical rule, you can kind of answer these questions. Because if we want to talk about the 60th percentile, we can talk about how that would look. So let's go over here to the David M. Lane applet. There's David M. Lane applet. It's a great applet. I'm sure this is what we use a lot. But people, if you've ever heard of Z-tables, people try to use Z-tables still today, but we have better technology. And I always like showing this because people say, well, you might not have this applet on you at all times. On my phone, I actually have the David M. Lane applet. Basically, I have the ability to do everything we're doing here on my phone.
Oh, wow.
Yeah, so I mean, I can do any of this at any time. It's better than a Z-table.
Sure.
So technology has made statistics better and more portable. So what we need to understand about the 68, 95, 99.7 rule is where those numbers come from. And the visualization here is great because if we do between, we can just type in 0.68 right here, and there's one, negative one, and positive one. 90 is actually 95.449, and you see now that says 2. We round it to 95, but if you notice, that's not actually, if you look down here, that's not actually 2.
Sure.
It wasn't actually 1. It's something like 68.26, and now that says 1 at the bottom. Because we do rounding to make it nice.
Okay.
And now 99.7 is very close, but it's actually 99.73. You don't need to know the exact numbers. You do need to know 68, 95, 99.7.
Okay.
That's what these are based off of. As you can see, 1 standard deviation above and below, 2 standard deviations above and below, 3 standard deviations above and below, 68, 95, 99.7. Now, the important part here is when we talk about the 68th percentile or 60th percentile in this question we see right here. This is where people get confused and they're like, I can't visualize it. But let's go ahead and use what we already know with 68%. And let's talk about right here at 0. How much percent of the data is below 0? What percent of the data is below 0? So we go right here to 0. What percent is below it?
Below 50.
50. And then 68 is in between here, right?
Right.
So what is 68 cut in half?
34.
That's right. And so now there's 34 inside of here, right?
Right.
And there's 34 here. So if we go from 1 down, you told me 50% is from 0 down, right?
Right.
And 34 is in here. At 1, how much percent of the data have we added up to?
We add to 84 or 24?
You're right, 84. If we go this way, it's 84. And if we go this way, it's what? 84 less than, 84% is less than that, and what's above it? If 84 is below it, then above it is, good?
16?
That's exactly right, because it's 100% curve. And
Okay.
that's how we're using the empirical rule. And now the question is, why does that relate to anything we're doing right here? Well, this question wants to know the 60th percentile. And with this in mind, the 60th percentile is somewhere between the 50th and the 84th.
Right.
So we want to find the 60th percentile. It's somewhere in there. So let's go ahead and take the David and Lane applet and put in the actual numbers. So we use the empirical rule idea to get an estimate.
Okay.
1,190. So I'm going to make this actually say the real numbers on there. So this is 1 standard deviation, 2, and 3, which we could put 0, 1, 2, 3 below this to see the z-scores. So with this in mind right here, when I put in 60 and I go below it, so I'm going to have to change it so it graphs below by clicking this button right here, it's going to show a line somewhere in here. We hit below, and there's the line right there.
Okay.
So using the empirical rule, we could estimate. We could say, well, it's got to be between 0 and 1 standard deviation above, because that's where the 60th percentile is. And you can't be exact, but you can get close, and you can get a general idea. And we do ask test questions like that sometimes, like, where would the 60th percentile be? We could say between 0 and 1, 1 and 2, 2 and 3, or above 3. And, some of those answers are kind of ludicrous if you look at it, but we'll get people answering between 1 and 2 often because they're like, well, I don't know. It's hard to tell graphically. But if you start marking the percentiles there, you can. And so I'll mention one last trick here that really helps. If you ever want to break down the normal curve, one of the best ways to break it down is to take 68. And then what is total outside of 68? Just total.
To equal 100?
Yeah.
So that would be 32?
And then if you cut that in half, what do you get?
16?
Yes, and that's what we do. You can break down anything outside of it using 68, 32 is outside, and then on either side is 16. 95, 5 is outside, and then on either side is 2.5. And the great thing is you can test yourself with this by going here and go to above 2, and we get something very close to 2.5. You can go above 1, and we get something very close to 16. And so you can do a lot with the empirical rule. It's so that's why I said it like a billion times at the start of that. It's so very important, and the homework's going to reinforce that.
Okay, great.
Yeah.
Okay.
If you have any more questions, feel free to ask, or I can do any part of the homework if you like.
I don't have any at the moment. Let me think. Just you don't want to see my bed. I've got papers all over it.
I've got like video game posters and stuff. Video games everywhere. It's like video games. Nintendos.
My children, they're playing the new Elder Scrolls.
Oh yeah.
Yeah. Of course, they're 20 and 23, so they're still children to me.
It's like, I'll show you a crazy thing real quick.
Okay.
I think I have 20 video game consoles now.
Oh wow.
There's 17 different ones, but you remember Atari, right?
Of course I do.
Yeah. This is an Atari.
I remember Pong.
Oh yeah, now Pong. That's this is an Atari Lynx. I got it at McKay's recently because they had it. Oh. But an Atari Lynx, because like the old Ataris, like playing games like that. This is a handheld, basically like an Atari Game Boy. Just think of it as that.
Okay.
Old Atari. But it came out, I think, in the early '90s. But that's when now I have every Nintendo system. I have every Sega system, I think. But I have around 18. If you name it, I have it, and it's like fun room. Like literally, there's literally Nintendos over there. Like you can see a GameCube over there.
Oh yeah.
Yeah, and then there's a Nintendo next to it, original Nintendo. So, yeah.
Oh, how funny.
What were you? Good.
I was gonna say, what do you do in your spare time?
Well, actually, I've been working on more YouTube stuff. I've got an app idea, I've got a YouTube idea, and then I've got the Boss Project, and then I'm taking a class, and then like I got my controller right here. I play a little bit of video games in my spare time, but usually, lately I've been lucky to get an hour or two in a week. It's just like it does become more of a collection. Like you can tell how much I play this because it literally still has the tags on it, and it doesn't. So it's It's just more of a like, hey, I bought something for my collection.
Yeah, more nostalgia.
Yeah, I think I've got 3 Nintendo Wii's in this room. I don't know. I've got like 2 Xbox. It's ridiculous.
What did I have? Sorry, I'm just looking here. I thought I had another one. With the JUMP program, do you like that at all, or is it?
It's so the good and the bad of JUMP.
Mm-hmm.
It is a little bit like Excel. Like it is kind of you look at it right here. Let's pull up an actual data set. Sending one of these right here. Okay, I don't like these data sets because we keep every time we've been sending out the projects to students, and we've been doing it like deleting stuff, and so I like this right here. JUMP is basically Excel on steroids,
Okay.
and so it's a GUI, graphical user interface, for anyone who doesn't know that term, and meaning you just have point-click buttons. You don't have to type in line commands, so that's really great. Just a lot of the simple stuff in JUMP can really help. One of the problems we run into is a lot of people won't have a JUMP license when they leave UT, so we're teaching them something. But still, we are teaching them how to use software that Minitab, SPSS, Stata, all these are basically the same. Like if someone has me work on SPSS, I'm like, oh, it looks like JUMP.
Okay.
But it's very, very, very powerful when you get into things that require kind of linear regression and eigenvectors and eigenvalues. There's a lot of cool things that we could not do with computers. Like if I want to predict one of my favorite things, because we're about to get to this chapter, that you can't do with Excel, is if I want to predict if someone's male or female, I can make a decision tree right here, and I'm probably including in some variables I shouldn't. Let's see if I did.
Well,
so this is actually everybody that we did surveys on. And obviously one of the best predictors in male-females is a person's height. And the females are blue, a little counterintuitive. I could reshade the points if I wanted. But the females are the blue points and the males are the red points. If someone is below 68 inches, you can look at the probability of them being female. We do think most females are shorter than males. But you do see over here, this would represent females that are taller, or excuse me, 68 inches or taller. And you keep splitting up the data. Height and weight are big factors in if someone's male or female, how many hours of video games they play. Amazing topics like R squared, which is percent of variation explained in Y by the variables of X. So a lot can be garnered from this, and we can create statistical models, and we can even do things like save the predictions from this model. So the power of JUMP is amazing because I can go here to save predicted formula, and it will actually predict for me, as you see over here on the side, whether the person is male or female. And then immediately I can go, and okay, so think of this question real quick. I want to explain if someone is male or female, and then I'm going to make a prediction if they're male or female. Both of those variables are what kind of variable? Both of those variables are what? If I ask someone, are you male or female, and then I make a prediction on them being male or female, both of those variables are what?
Categorical?
Exactly. So it goes to chapter 3 now. If I do a categorical bivariate display, what am I going to get? What kind of display is a categorical bivariate display? Think of the Titanic stuff. If I display that in a visualization with blocks type stuff.
So it's a box histogram?
That'd be quantitative. Histogram is quantitative. So think of stacked box plots, but the really cool one that we like. Think of little pictures inside of little pictures. We call that a what? Like when you think of all the little pictures that make up a big picture, it's a what? It's a photo.
I forgot.
Okay, plot. I always try to like make people think of the words. It's like
I'm sorry.
I don't mean to put you on the spot. I was like, what I try to do instead of saying stuff a lot of times, is I'll try to have my students like think of the word, like think of it. But a lot of students will sometimes get nervous. I'll be like, oops. I was like, what is 10 minus 3? And they're like, and I was like, just 10 minus 3. Like, think about it. And they're like, and then I'm like, I could tell they're so nervous. I'm like, oh, it's 7. Like,
yeah.
I think a very simple question, very like nerve-wracking. But a mosaic plot is a bivariate display of data. And we see here, this is our ability to use our prediction, which is down here, Like, how well does our prediction explain someone's actual gender? You can kind of see where we missed. These were females we predicted to be male, and these were people we predicted to be female who were actually male. These were people we predicted to be male who were actually female. And it's kind of cool to realize we really didn't miss that much. If you look at how many we missed, it would be 47 and 39 out of 862, which is, we only missed about 10% of the time.
Right.
Which I think if you think about it, it's pretty easy to explain. If you say, how tall are you? How much do you weigh? Things we generally think about that explain differences between male and female. And that doesn't mean we explain everything, because we'll get into R squared and everything later on. We're not able to perfectly explain, and I always kind of find it fun in class because I usually have people do this, and we try to figure out why we missed, because there's a lot of reasons to miss, and because not everyone is the stereotype. Statistics is not like the bad types of stereotypes. It's just about what on average do we see in the data? Like what is usual in the data? So it's not a stereotype like, oh, people do this, because everyone can break away from it. We can be wrong with statistics. It's just kind of like on average what will happen. So we shouldn't, I don't know, it kind of gets in this whole bad, like, I don't know. I always hate when I bring some class because I don't want people to be like, oh, you're saying all people do this. No, it's like on average, like, do you agree with me? On average, a guy will usually be about 5'9". On average, do you agree with me? A girl will be about 4'11". Do you agree that usually people are different in height depending on male-female? Okay, well then we can explain usually, and that's exactly what we're getting to in this class. That explains a little bit of gender. I love it.
Yeah.
So
it's not making assumptions as far as,
Exactly. It's just, and that's the thing is like, you're right, because if we said, oh, you must be a guy, no, it's like the probability is likely due to these factors, but anyone is capable of breaking away and being an individual in this model.
Right.
So, I love it. And if you look at this, it does a really good job. I can use more variables. We get into weird stuff down here that probably doesn't work. Like, no, we haven't hit. I can make it weird or crazy if I hit here. It keeps going to hours of video games, which is a pretty good. Have you driving and out of gas if you ran out of gas while driving? But this is a later variable, and if you even look at it, who is the guys are more likely to, because the guys are the red. But this is only taking into account 30 people. If you look at this, there's 10 people here and 30, because every time we do a partition model, which we'll learn later on, you're dividing the data down further and further, and there's a lot to this model that I haven't talked about because I'd be basically teaching this lecture. But things like this we couldn't do in Excel. Maybe there's a package in Excel I don't know of, but JMP has everything all in one. And Excel is getting better. Excel is, you can do a lot in Excel. You could do 80, 90% of this class, but JMP is a little bit more powerful in a lot of regards. So.
I agree with that driving without gas. I know a couple who do.
A couple guys who do that?
Oh, yeah. My husband's run out of gas 3 times.
Oh, no.
Yeah.
Here's the cool thing is we could just do this because this is only a small set of the data. Driving without gas is variable 36. We have the numbers on these. So let's see how well it does. Let's see if it's statistically significant. This is later topics. But this is the fun of JMP. Oh, wait. You're right. Oh, my gosh. It's statistically significant. Look, and this just gets back into mosaic plots, which was chapter 3. The bigger the gap, the more significant. And here's something that we don't talk about because it's more advanced.
Oh, no.
If you imagine if we talked to like 3 guys and 3 girls. So we just talked to 3 guys and 3 girls. So let's do this data now. We have male, female. Let's just call it gender, and then we have out of gas. So we need yes, yes, no, no. And we're going to have male, female, male, female. So we have 2 guys have said they've ran out of gas here. 1 female says she's ran out of gas. 1 guy says he hasn't. 2 females says they haven't. So if you look, there's 3 males total, and this is just the frequency. You won't have to do stuff like this on the test, no worries. But this is just a data set now of how many people have answered this question, male, yes. So there were 2 people who said, I'm a male and I've ran out of gas. So if you look, there are 6 total people in this data set. There are 3 total females because you'd have to add up both these columns, and then there are 3 total males. You can look at how many people have ran out of gas. 3 people have ran out of gas, and 3 people have not ran out of gas.
Right.
So now let's go ahead and do a bivariate display of this. If we go here to this right here, and we say gender, does gender explain running out of gas? Or we did it reverse, so let's do this. Does running out of gas explain gender, which either or will still have the same relationship. I'm going to put in the frequency here because that's how we did the data. So this is a humongous gap. Okay, this is a little bit more advanced, so don't worry about it. I don't want to confuse you.
Okay.
But here's the thing. On a test, for anyone watching this, would that be like we have a relationship or evidence of an association? Does that mean something that the two have a relationship? Would that be something of a relationship right there, or significant?
Well, yeah, they're about even if you add up.
We'll just look at the difference in the heights right here to see if there's a difference between male, female on, or yes, no on male, female. Does that look like a big difference?
Not really.
In the basic sense, yes, but you might be, I think you're thinking beyond because you realize that is a difference of 1, right?
Right.
Now you're thinking like the complex way, which is good. The simple way is this is a big difference right here, but in the world of statistics it's not, because it's only based on 6 people where there's a difference of 1. Now this one over here is based on 862 people. This difference, which looks smaller over here, is actually significant. And we can scroll down here, and you were right. This is what we call statistically significant. More on that later. If I hover over it, it should say, like, this difference is significant. Let's see if I can get it to say it. Come on, John. If you have to, like, circle it. There we go. See, it says it can indicate very convincing significance.
Okay.
So it's telling us this difference is significant. More on that later when we get to p-values. But this is the hard thing for people to understand sometimes, is in statistics, how much you sample will kind of denote how significant something is. So this over here is actually not going to have a small p-value. You see, it doesn't have any sort of thing to tell me this is significant. Actually, I think it will tell me it's not significant. Is not significant right there. P-value is not significant, telling me this could have all happened by chance. So we don't just look at something and say, oh, that's a big difference. We have to take into account how many people were sampled.
Right.
Here, you were actually right to tell me that there's an association between someone being male, female, and running out of gas. We have data that kind of shows that. Now, what's interesting is I've never ran out of gas.
Okay.
So, male, no. And we see there's a lot of males who say no. There's some females who say yes. But the percentage of males who say yes is greater because there's a change in percentage. Like when we go from yes to no, there's more males saying yes than females. And that's when we switch right here from this to this. We see, oh, the males goes up and the females go down. Not all males run out of gas, but there is an association that males are more likely to run out of gas. So there you go. That's how I think in the statistical world.
Okay. Well, and I took probs and stats when I went to Walter State, and I know that I remember that if it's, let's say, the people that you survey or what you survey is less than 100, it's not as accurate unless it's above 100 or something like that. At least 100 people for a more accurate.
That is kind of true.
That's just what I remember for some reason.
A lot of statisticians like to come up with numbers like certain amounts we need, like later on we'll talk about NP/NQ conditions, success failure conditions. And so what they're probably talking about is the reliability of whatever you're calculating, and that the standard deviation or the standard error might be too high. And we do have corrections for those. Like the t distribution can be used as a correction. We'll talk about this stuff later on. I'd be interested if you find that where someone says like you should really sample 100 to get an understanding.
It was just in the textbook that kind of gave an idea of a sample of 100 or larger is a better, will give you a better view and a more accurate view than anything less than 100.
And I think that brings up a good point because a lot of times you reach this point of understanding with your sample. Like if you sample 1,000 or 2,000, you your idea of what's going on and your estimates won't change that much. Like if you get 1,000 people and 1,000 people and it's representative, and then you double that to 2,000, you're probably just wasting time and money. But if you get a sample of 50 versus a sample of 100, the understanding you gain and the strength in your statistics is worth it.
Right.
So multiplying by 2 doesn't strengthen the your knowledge of the statistic by 2. And if you look at the formulas, there's a diminishing effect of sampling more and more. Because you can think of like, if I go out and I sample, I talk to 2 people at UT versus talking to, 4 people, it's like the distribution starts to become less and less on those individuals and more on the averages. Because 2 people, if one person says, oh, I have a 0.15 GPA or 0.5 GPA, all of a sudden we're going to skew towards them. But once I get up to like 10 people, that 0.5 is going to be averaged out with everything else, and the effect of individuals becomes less. So when you're at 1,000 going to 2,000, you're really not having individuals destroy your distribution. And as long as you sample representatively, that's the biggest thing, then a sample of 100 is pretty strong in most cases. But statisticians love, or at least books, love these numbers like, you should sample 100. And it's like, well, I mean, like, what do you want your standard deviation or standard error of your estimates to be? What are you trying to, how important to you is it? How much money do you have? How much time do you have? These are the real world business analytics factors we have to think of. Because 100 is great, but it's not perfect. I mean, you can do it
sure.
times. Yeah.
Okay.
Awesome. I like questions like that. They make me think. I'm like, wait.
Well, great.
Awesome. I don't know. I hope other people, you can ask more questions if you have them. It's probably like, I don't know. Like, I just literally like reading news. I was like, so.
Well, I should probably get my homework done considering I have some due this evening.
And you know of the YouTube videos, right? Have I asked you that?
I do. I have subscribed to your channel. So and that is very helpful because you go over the same homework problems that we're doing. So
there's here and there, but mostly.
Yeah, definitely they have helped. I appreciate it.
Awesome.
But yeah, I think I'm good.
Cool. And if anyone has any ideas, like if anyone watching this, because I will post this, if anyone has any ideas for videos or is like, hey Brian, can you redo this? I mean, I might redo videos because I do have, it's interesting to me, the voice quality. This is my good mic right here, and it works really well when I do like the recordings, but apparently on the Zoom meeting it might not work as well. Maybe I'll do some tests. But
you sound like you're closer on this one, so to me I think it's a little better, but that's mine.
I used it in the last Zoom meeting with another class, and it actually didn't sound as good. So I'm going to see how this one sounds and compare it, because you were right, because when I put in the mic and I listened to it, I was like, it doesn't sound like my recording stuff. So yeah, I'll be checking it out and seeing which one I like. But no, I appreciate you helping me out with the mic situation, because this one, I think you might be right that it sounds better without the mic plugged in.
And one thing I thought was funny, I just have to point that out. I like how you corrected your spelling of homework on the videos.
Yeah, that's early on. Oh man, that
was funny.
Oh yeah, no, because like students emailed me and I can't change. Actually, now I'm good enough now that I could go in and rechange that title card. Because, what did I say? I wrote something over and I was like, oh, I finally got it right or something. Like
yeah, you had an arrow going up to the E, and you said, I learned how to spell.
Yes,